Yeah, seconds. No, still not. Okay, so technical difficulties aside, so I want to talk about new solutions to Petrov Type D equation with Riemann symmetry, and maybe let me elaborate on the title a little bit before. So what is the Petrov Type D equation is probably the question. I will be coming to that precisely, but let me for now say that solutions to Petrov Type D equation essentially determine the geometry of isolated horizons. And isolated horizons, I will be also coming more precisely later, but however, they are local generalization of Killing horizons. So essentially, I want to talk about some new isolated horizons that we have constructed, which admit U1 symmetry. So going from the bottom, the two new types of horizons are first the horizons admitting structure of a non-trivial U1 bundle over some higher genus surfaces, whereby higher genus surface, I mean that they have genus higher than 0. So essentially everything apart from a sphere. The other class are horizons which also admit structure of a non-trivial principal bundle. However, their bundle action is generated by a vector field which is not the vector field which is null at the horizon. However, it's transversal to it. And this definition might seem a little bit strange, maybe a little bit forced. However, it actually appears quite naturally as a horizons in the Kernat ADS spacetime, which are interpreted with this U1 bundle structure in mind, such that they are made non-singular. So this will be the thing that I will start with. So all of those non-trivial U1 horizons appear naturally in that spacetimes, and I want to talk about also embedding of those horizons. So so those horizons appear in Kernat ADS, and Kernat ADS itself is a subset of the large so-called Plebański-Demiański family of spacetimes. And they are very interesting in themselves because they are the most general Petrov Type D solution in 4 dimension, meaning that Petrov Type D means that the value tensor has two double principal null directions. And they are the most general solutions to Einstein Maxwell equations, possibly with lambda in 4-dimensional fields, such that the electromagnetic field is aligned with one of the principal null directions. Of course, the main reason why they are so widely studied is because those space-time, this family generalizes all of the most widely studied black hole solutions, such as Schwarzschild and Kerr. And this generalization is can be thought of inclusion of more physical parameters. So in general, there are seven physical parameters in Plebański-Demiański spacetimes. Those are their customary names. However, out of those 7, I think only 3 of them really admit like a clear-cut physical interpretations. So those would be the electromagnetic charges and cosmological constant, because, well, those parameters simply appear in Einstein Maxwell equations. So 2 of them, which I will be referring to as mass parameter and Kerr parameter, usually are said to have something to do with conserved charges of the 2 commuting Killing vector fields that appear in Plebański-Demiański spacetimes. So one could be thought about as time translation or some kind of boost symmetry, and the other is usually taken to be rotational symmetry. So in this context, the mass parameter has something to do with the conserved charge of the boost and the curve with conserved charge of the rotation. However, your mileage may vary case by case. So usually it turns out that actually these conserved charges are only like proportional to mass or mass time curve parameter. So whoops. The other is there's also the acceleration, which is thought usually about existence of some kind of cosmic string, which is pulling on the space-time, the black hole, making it accelerate. And this tension of this pulling cosmic string usually is thought of that it has something to do with the conical singularity existent in the space-time. However, as I will show briefly, this is also not so easy to interpret. And finally is the nut parameter, which is notoriously difficult to say anything sensible about physical interpretation, apart from the fact that it introduces many kinds of topological problems in the space-time. So I'll be coming to the nut parameter often. Also importantly, although the spherical case is most widely studied, there's actually no reason why we cannot impose other topologies. So it's possible to impose such identifications that in those space-time appears a distinguished family of two-dimensional surface with curvature, which is either.
What are these surfaces? Two-dimensional surfaces?
You mean what kind of surfaces they are, or
how distinguish these two-dimensional surfaces in four-dimensional spaces?
Well, this is of course a problem. Usually this is done by choosing some coordinates, and in these coordinates you can see that going to some subsurface, submanifold, you have something that is flat or hyperbolic.
But they have interpretation of the section of horizon?
For example, yes. And this zero curvature and negative curvature are of course important for the purpose of embedding the horizons with higher genus. Okay.
Excuse me, I have a small remark, not principle, but principal null direction. This is the correct name in English. Not principle, principal null direction. This is the, there are also principal directions in geometry, but not principle.
But in the second one, it's correct.
So I can barely hear you. Oh, so, yes, sorry, this is a typo, of course. This is meant to be the same word. Okay, so the nut parameter usually is thought about introducing some kind of a conical singularity to the space-time, where the conical singularity is some kind of an angle deficit. However, I think that in the space-time, this quantity is not so well understood compared to the case when we have only a two-dimensional surface. So let me elaborate a little bit on this fact. So it's useful to detect conical singularities. It's useful to distinguish two types of Killing vector fields. So those would be the axial and cyclic Killing vector fields. So cyclic would just mean that their orbits are closed, and axial meaning that they vanish at axis. And you might ask me, what are the axes? And of course, I could tell you that axes are surfaces where some Killing vector field vanishes. So to avoid cyclic definition, we have to either specify, we usually specify where the axes are, and then we look for the axial Killing vector fields. And this vanishing at the axis is important because usually we detect the conical singularity by this circumference to radius test. So as we tend to the pole, we expect on a sphere that the circumference to radius would just simply give us 2 pi. And if this phase to be 2 pi, then this means that we have either too much or too little angle. And of course, if the unit vector field does not vanish, then we get just infinity here. And those two types of vector fields are actually those two notions are actually independent of each other. So we could have cyclic Killing vector fields which do not vanish at all. And unfortunately, it happens that we can also have axial Killing vector fields which are not closed. So this poses a problem in which way we actually calculate this conical singularity. So I want to discuss it on an example of the tau-NUT spacetime, which is probably the simplest member of this Plemański-Demiański family with a spherical sections and the NUT parameter. So this is just a one parameter generalization of Schwarzschild. And we expect to have axis which consists of 2 poles, of 2 axis parts. So one would be the theta equal to 0 and theta equal to pi. So for theta equal to 0, because we have chosen the phi coordinate to be closed, so it's no problem. D over d phi is both axial and cyclic. However, because there's this term present, this 2r cosine theta minus 1, if you calculate the norm of psi of d over d phi at the other pole, you get something that does not actually vanish. So to remedy this, you can maybe add some contribution from d over dt, and then it would turn out to be axial at the other pole. However, the problem is that now this Killing vector field is not cyclic. However, as it's shown in this picture, it actually spirals. So d over d phi at one pole is okay. However, after addition of this theta, we actually have this spiral in the direction of d over d dt. So usually to do this test, we would just pick some closed loop and just integrate the circumference. However, here this is a problem because, well, we don't know along where we should stop the integrating. So one idea would be to just stop when we are at some point which is in some sense above the starting point. And of course, the precise way of stating where is the above is that we follow the d over dt Killing vector field. So the way of rephrasing this would be to say that we project this d over d phi to the space of the orbits of d over d dt. So we actually project the spiral down to the same Killing vector field as before. However, now this conical singularity is actually calculated in not in a spacetime, but in the orbit space of d over dt, and this is precisely the construction I will be showing you in a second. Yep.
Vanishes in terms of norm, yes?
Yeah. Okay.
In terms of norm calculated with respect to the metric, yes?
It vanishes in terms of the norm. However, yeah, you can actually it is 0 because the axis is actually Riemannian. So okay, if you go to theta equal to pi, you get actually a Riemannian positive metric. So if you have a Riemannian metric, if you have a positive definite metric, then if the norm vanishes, then the vector field must vanish also. So this is of course a shorthand. So we want to apply this to the general accelerated tau-NUT ADS spacetime, which I'm presenting you in the form of similar, those are essentially Boyer-Lingvis coordinates. And maybe the exact form is not that important. The important part is that we have this polynomial Q, which determines the position of Koenig horizons. And also we have this function capital A, which has the same term as on the previous slide. And well, it doesn't vanish at one of the poles. So this fact makes this one form omega actually being not continuous at one of the poles, which you can check by using some Cartesian coordinates that it's actually not well defined there. So this means that in the spacetime there's a singular half-axis, which one way of interpreting is, for example, to put a infinitely thin source of angular momentum along the singular axis. And the other proposition comes from the Misner, from Misner, who proposed his interpretation in such way that his observation was that if you perform this coordinate transformation, introduce this T prime, then actually the omega changes its behavior. So instead of minus, we have plus here, and now the theta equal to 0 is singular. However, the other pole is completely fine. So his idea was to just take two copies and glue the non-singular parts. However, to do this, if you really insist on this completely non-singular picture, then you have to agree that this T coordinate transforms in this manner as it's written here, which implies that actually T is cyclic. And this is exactly the model of the U1 symmetry that appears throughout this presentation. Okay, so maybe the other thing that it does is that if T is cyclic, then this Koenig vector field also actually is not only axial but cyclic. So this is also like an additional benefit. Okay, so the construction, how the construction works is that you could actually impose a U1 principal bundle structure in the entire spacetime. So the spacetime, the topology of the spacetime becomes S3 times R. The group action is generated by d over dt. We have said that its orbits are closed, so the group must be one. You can check some technical properties that it works. And the important thing is that this group structure, this principal bundle structure gives you a decomposition of the metric tensor in terms of some objects associated with this bundle. So first of all, we have this one from omega actually is proportional to the U1 connection of this bundle, and this Q metric is a metric induced in the base space, which this base space is just space of the orbits of d over dt. So we have actually essentially made this projection downstairs from this picture here. However, it turns out that this Q, because now we are in the space of the orbits, we more or less know how to calculate the conical singularities. It turns out that it has that this S2 has conical singularities. So this is far from a non-singular interpretation yet. So the next step would be to actually realize that we don't have to do this construction for d over dt. We can do it for a generic combination of Koenig vector fields, which are parameterized by this constant b. So essentially, what we are doing is we are looking for such a space of the orbits, for such a Koenig vector field that would give us a space of the orbits where there wouldn't be any conical singularity. And you can write the conditions for those conical singularities to be the same, and you arrive at this equation, which is convenient because only parameters of the spacetime and this b parameter which chooses the the congruence appear here. So this can be easily solved. However, what is the point is now that this vector field is not necessarily the same as the one generating the horizon. So even though I could claim that the spacetime itself is non-singular, I can even give you the coordinates in which it's apparent that this spacetime is non-singular. And the horizon itself as a 3D manifold is non-singular. However, its space of the null generators, because we would have to do quotient by a different field than we have than psi, it's actually only locally defined. And even if you would insist on extending this locally defined space of the null generators, we would see that this is a sphere with conical singularities. So this is the reason why we consider those types of horizons. Let me maybe tell something that I think is quite interesting about this condition for vanishing of the conical singularity, given in terms of these functions p. So this parameter b, which essentially chooses a congruence of killing vector fields, which is just like a choice of a different co-rotating observer, it appears only multiplied by the knot parameter. So if the knot parameter is 0, then the denominator vanishes, and this condition is either satisfied or is not satisfied for any of the observers of this type. So this would mean, for example, that in Kerr, every observer says that there is no conical singularity. However, in symmetric, which is like accelerating Schwarzschild, every observer agrees that there is a conical singularity. However, now it seems that if the knot parameter is present, then not only all of the observers of this type would say that the conical singularity is something different. There's also some distinguished observers which say that, well, there's no conical singularity at all. So if you want to associate the presence of a cosmic string to existence and of some conical singularity in your spacetime, then I think this becomes problematic if the knot parameter is present. Okay, so going to the
Later against Petrov, if you be 1 over 4p, then the field of integral.
Yeah, I think this is just an artifact of the coordinates that we have chosen, because if you do this in different coordinates, then I think this would correspond to psi, which has just d over d phi. So this is something like this. There isn't, I think, any more secret observers hiding here. Yeah, because of course this parameterization doesn't capture all of the Killing vector fields. I mean, all of them except for one. Okay, so knowing the motivation, what are actually isolated horizons and what is a type D equation? So I want to present maybe not the most standard definition of isolated horizon, because for the purpose of stating what we are doing is enough to speak about horizons which are unembedded 3D manifolds. So there are several steps in this definition. First of them is just a non-expanding horizon, which is like a three-dimensional or just a codimensional null surface. I mean, codimensional if it would be embedded. However, it's not embedded, so it's just maybe three-dimensional. With degenerate metric Q, and we already assume that it has a topology of some bundle over some compact two-dimensional surface with Riemann metric Q, and this is maybe generalization of the of the standard notion where one would say that, well, this bundle is trivial and it's not over any compacts to the surface, it's over a sphere, and fibers of this bundle are not generic, but they are just translations. So then this would give us this maybe standard definition. We require that any null field satisfying this condition is actually a Keening vector field of this Q metric tensor, which justifies the name of non-expanding. And of course, because H is null, there is no unique way to find the connection, and it has to be given externally as a part of the definition. We just require that it agrees with the metric connection on the Riemannian part. So then, isolated horizon, we add the constraint that this is something that's usually called being stationary to the second order, is that this given connection commutes with the flow of some representative of this specified class of null fields, where this class of null fields is given simply by rescaling by a real number. So this is quite restrictive, and also an important value that will be appearing is this rotation one form omega, which essentially encodes the part of the connection that's not given by this metricity condition. We can define the surface gravity in the same way as for the Keening horizons. However, because I haven't actually said anything about Einstein equations, and this kappa has to be assumed to be constant by hand. So if you would have some Einstein equations, then this is a consequence. However, so far we just put it by hand that kappa is constant. Yeah, and the last important component is that we have the omega, which is like a pseudo-scalar rotation invariant, which is calculated by taking an exterior derivative of omega, and this eta is a surface form associated to Q. And by these tools, I mean that you have to actually take the pullback to some local section of the horizon. Okay, and so for isolated horizons, we end up with the fact that this omega is actually uniquely defined, and L and kappa are unique up to real constant. So it's enough for us to say that the horizon is either extremal or not extremal, depending on whether kappa vanishes or not. So so far I have told you that those horizons that we consider have the structure of a fiber bundle. However, it can be said even a stronger statement can be said that this is actually a principal fiber bundle, where the action is, of course, what we expect. So it's generated by the flow of this null field. Because, well, this is just one-dimensional, so it's either translations or rotations. So this gives us some possible way to maybe start classifying those horizons. And can check some technical conditions that we can define the boundary connection in this way, where the omega tilde is omega divided by surface gravity, just for the purpose of normalization, and this L star is the Lie algebra element associated with the vector field L. You can similarly define the bundle curvature, which, if you compare it with the last slide, has something to do with this pseudo-scalar invariant on capital omega. And this is a convenient construction because now we have two different characterizations, I mean, topological invariants of our Riemann bundles. So first of them is so-called Euler characteristic, which is just 2 minus twice the genus. It should be 2 pi here also, sorry. Which you get by integrating the Gaussian curvature over the slice of the base space. And the second one is the Chern number, which you get by integrating. Well, actually, you integrate a local pullback of a bundle curvature, which can be expressed by this pseudoscalar invariant omega.
If you just because of your notation, maybe you meant something else, but this is omega 2. Omega 2 in the previous slide, it was related to this.
Oh, right. Sorry. Yeah, you're right. There should be probably kappa here. Yeah. Okay, so the Petrov Type D equation what is the Petrov Type D equation? So of course by this type D we would mean that by the horizon being type D would mean that the Y tensor for an embedded horizon is of type D at the horizon. However, it can be stated even locally in terms of this invariant quantity constructed from the Gaussian curvature and omega and some constant. That if this is non-zero, then such horizon would be embeddable as a type D horizon. So to state the Petrov Type D equation, is probably most convenient to introduce some null coframe on S, and then this is a partial differential equation on this invariant of the horizons, where of course those are generically those are functions. So if you solve for those guys, then knowing what topological assumptions you have assumed, you can actually construct the entire horizon. So this equation has been, as you can see, solved at our chair very religiously for the last couple of years. So I think that all of the cases which are not difficult are mostly taken care of. So in case where this is a Riemann surface with genus higher than 0, however, the bundle is trivial, this has been already done. So we have only generalized it to the case where this bundle is non-trivial. This case of sphere times R are essentially like horizons in Kerr. Those with Hopf bundle structure are horizons. Well, they appear in Taub-NAT, and there are some distinguished class in accelerated Kerr-NAT ADS spacetime. This fourth part is the thing that I will be speaking in a second, together with this fifth bullet. And I think that if you're looking for some hard problem, then definitely saying something about spherical and non-axially symmetric solutions is still an open problem. Okay, so what are the new solutions finally? So first, the horizons with bundle action transversal to L. So as I said, those are the horizons modeled on the horizons appearing in the accelerated Kerr-NAT ADS. So how do we construct them? Well, we take the two patches of horizons, or maybe just two horizons, or we write it in two patches. In such way, for the one patch is equipped with such metric that if you go with theta equal to with theta to 0, then this component of d phi squared would actually go to 1 at the pole. So the pole at theta equal to 0. So we'll just reproduce the spherical metric in the neighborhood of one of the poles. And this rescaling can be always done because, well, you can always rescale just to scale locally the coordinate. You take the other part where the situation is the opposite. So the other part is non-singular. The other pole is non-singular. And we impose this transition map between those two parts. And this should be familiar already, especially this third guy, because this is essentially the Misner transition map that I have shown for Kernat ADS spacetimes. So so yeah, of course they are modeled on this construction is modeled on horizons of topology of a free sphere, which however only one of the right and left invariant Killing vector fields for free sphere are actually killings of this horizon. And here in those coordinates, which I guess maybe using the coordinates isn't the most general way. However, this is definitely the most convenient way that we have found to present those horizons. And the U1 action is generated by d over d game for those horizons. There's also some technical things that this rotation one form calculated for this L has to be well defined in both of those maps. However, it turns out that this can always be done by choosing some specific surface gravity. Okay, so this was the topological ansatz for this construction. We want to actually solve the type D equation for such horizons. This is most conveniently done in some complex frame which is adapted to axial symmetry. And in the axial symmetric case, this type D equation is actually maybe it's simpler because it reduces to just ODE, just ordinary differential equations for these scalar invariants. So one thing that has to be specified, because we work in coordinates which are in principle not defined at the poles, is we have to say what actually happens there. So first of all, there's this assumption that P vanishes at plus minus 1, where plus minus 1 correspond to the poles. And this is the intuition behind this is that, well, at the poles, that we want there to be two poles, something resembling a sphere. So and it turns out that this is actually everything that you need to characterize those horizons is just this condition. However, we do not assume continuity, which is usually given in terms of this derivative of P, taking some particular values. So we allow for this S to have conical singularities. And it turns out that there are two classes of solutions. So first of them are with omega equal to constant. And it turns out that if omega is constant, then actually that this continuity condition is always satisfied. And it turns out that those are the same horizons that were derived previously and shown to be embeddable in tau-NAT ADS. And the second class is a little bit more interesting. There are actually 5 parameters, so A, B, C, D, and R squared, which are free. And those are, so the precise statement is that all of those horizons that appear in accelerated Kernat ADS that is interpreted in this Misner type interpretation can be expressed as one of those horizons. So actually, so this is maybe the first option, that you take this solution and you go through this construction I have showed you here, and you arrive at the horizon which has this structure of one bundle with an action transversal to this field L. However, of course, it's up to you what you construct from this those invariants. You can also take just take this S to be a sphere with conical singularities and just construct like a regular, regular in the sense that this standard horizon that people think about, and I think this is also possible. Okay, so the other case, the other type of the horizons are the horizons of higher genus sections, which, as I have said, has been already solved in the trivial, of course, only in the sense of topology trivial case. So it was assumed that they have a topology of the product of S times real line. And S is for us just a smooth oriented compact Riemann surface. Essentially, we assume everything so that those surfaces can be characterized only by genus. And what has been found is that if you solve the Petrov Type D equation, then you get that both the Gaussian curvature and this rotation pseudoscalar are constant, and actually the omega is not only constant; it has to vanish. So the authors also provide us with some special toroidal case in which it's easy to exhibit coordinates. So because kappa is constant, then this has to be just a flat torus metric. Well, actually, in torus case, this case is also 0. So yeah, this is just a flat torus metric given in coordinates psi and phi, which just span two circles from which you can construct the torus, and the omega is well, it's just essentially a closed form on a torus because it has to satisfy where it is. It has to satisfy this equation with omega equal to capital omega equal to 0. Okay, so in higher genus, this is a recurring theme for those type of horizons. It's quite difficult to say anything using coordinates, so you can just resort to saying what kappa, what k is, and k is connected in this case to genus of S and the area of the calculated using the metric given on S. And yeah, here you can see explicitly that well, genus is 1. So if we have torus, then case, what we expect is just 0. Okay, so it turns out that in non-trivial case, the story is very similar. So we still find that k, that Gaussian curvature is constant, that omega is constant. However, now there is no constraint that omega is equal to 0. And actually, we want to exclude this case because omega 0 gives us the case of trivial bundle. So there's a natural question, namely having those invariants and knowing the topology of the section of the horizon, the question that comes to mind is probably how many different, from those ingredients, how many different horizons or how many different bundles we can construct. And luckily, this question is answered by the general theory of principal bundles. And it turns out that those classes of isomorphisms are just the same, isomorphic to the second cohomology group of the section with coefficients in Z. Long story short, if S is such as we assumed, that it turns out that this is just Z. So essentially, we have a horizon for any, we have a bundle or a horizon for any natural number, even integer. So, and the omega is defined, of course, by again this condition condition here. And I was given not only up to gauge, but also up to the one forms which generate the first Ramp cohomology group. So let me maybe again, this can be done explicitly for the torus. However, maybe just in the interest of time, let me skip this part. And the conclusion would be that
phrase that this only is defined up to each transformation. One for so I would say that if we add some one form from the Riemann cohomology, then we have a different form. Right?
Yes.
Like gauge, that is the same.
Yes. I mean that this equation is still satisfied for. Yeah, this is a different solution. I will actually comment on this. Yeah. Okay. The same. Yeah, adding something from the Ramp cohomology group actually changes the horizon globally. Okay, so let me skip the toroidal part. Maybe just saying that in the non-trivial case, we can essentially express this invariant omega in terms of a Chern class of the horizon and surface gravity and area. So the question comes to mind whether this is just a mathematical curiosity that we can solve this, or do those horizons appear in some space-time? And perhaps unsurprisingly, if you have been following from the beginning, we have some kind of a NUT type space-time as a candidate, and they are so-called generalized type NUT. Generalized in the sense that we have this additional parameter epsilon, which determines the sign of the curvature of this distinguished family of two surfaces. So if it would be equal to 1, then after some change of coordinates, we would just get the tau NUT solution, or putting L equal to 0, just Schwarzschild it. However, we can still do two other cases. First is the epsilon equal to 0, in which this is a metric on a plane, and we want our horizon to be compact. I mean, our slices to be compact. So we can construct from the plane torus just by taking quotient by some two-dimensional grid on the plane. And the third case actually encompasses all of the. So here we have genus equal to, for epsilon equal to 0, we have genus equal to exactly 1, and hyperbolic case takes care of all of the genuses higher than 1, so from 2 to infinity. And well, it follows that all of those surfaces can be constructed as a quotient of hyperbolic plane by some group. This PSL2R is essentially a group of symmetry of the hyperbolic plane, so just quotient by some subgroup of symmetries. So because we couldn't really use the coordinates, then we have assumed that we have a space-time which is which has the structure that we really seek, so that in this space-time exists some mu1 principal bundle over this surface S, which has the same properties as the same topology as for the horizon that we wish to embed, and we assume that this A is a connection of this bundle, that it satisfies the same thing as for the horizon, and it's actually, it turns out that it's enough to embed all of those horizons. It's enough to write the metric with ansatz as here, and solving the Einstein equations. It turns out that what you get is that this function f appearing here is the same thing as in the generalized tau naught. However, we have explicitly those compact sections appearing here. So the solutions are just like locally isometric to generalize tau naught. However, with compact topology of the slices, and you can work out that the horizon is actually embeddable. You can find the space-time parameters which have to this constraint on space-time parameters to embed the horizon with some given pseudo-scalar rotation invariant omega. And maybe the last comment would be that of course this bundle structure extends in natural way to the bundle structure given in the entire space-time. And here's the comment that all of those, whenever we have a non-zero de Rham cohomology group, this A is only defined up to the members of this group. However, they are not, and they can be locally. They can be added simply by a coordinate transformation. However, those coordinate transformation usually do not extend to a global the global coordinate transformation. So this could be probably seen even for a torus. So those guys, this AD phi and AD psi. So psi and phi are only local coordinates because they are discontinuous in 0 or 2 pi equivalently. Yeah, so this has been sometimes called like a gravitational Aharonov-Bohm effect, in which the spacetime is locally the same, however the global properties are different. Okay, so I think I'm just right in time, so thank you for your attention.
Can you show the previous slide?
Yep.
Question?
If you have this, probably make it, but if you have this Petrov Type D equation, you just throw dimensional equations on the horizon, yes, and then can you show that you can extend this solution to the whole space-time somehow and see what is not good.
Yeah, I think that this has been done by Raj, for example, that if that type D horizon is, I mean, space-time around the type D horizon is also type D. Yeah.
But I think the question would be, what would we do? I think the question was what we did. So that we solve the equation with horizon and then found space which contains.
Yeah. I mean, if the question is whether this horizon is necessarily embeddable somewhere, then I don't think this is true.
Are these solutions vacuum solutions?
Yeah, everything is electro lambda vacuum. So I mean, for the isolated horizons, this is of course without charges. So this is just lambda vacuum. There are type D equations implied by lambda vacuum Einstein equations.
Okay, thank you again. To jest już właśnie coś popatrzeć na to.
Tak, tak, znaczy sekundkę.